Okay. Right. So yeah, last time we basically we just started with controls and made sure that the character can move with WASD, and today we want to get some animation there, make sure that he has the idle animation and the walking animation, and we want to make him look in the right direction with either animation, and then afterwards we're going to play around with physics a little bit and make sure that there will be some obstacles on the level, and then the character will not pass through the obstacles and stuff like that. And we see how far we get. I mean, we can do stuff like interacting with chests and stuff. Let's see how far we can get in the roughly 2 hours, I guess. Okay, so so we're going to start with the animator again. Last time we had some problems with getting the correct animations to play, so we're just going to start off from there again. So what we want to do is we have an idle animation and a move animation, and we already set up 2 parameters here, the direction X and direction Y, and we also need a third parameter, a boolean called isMoving. We actually had that last time. I think I just deleted it. I'm not sure why. So yeah, so the animator basically gets values from the from our view class. So just a quick recap: we have the model view control system where the model is responsible for the actual movement and how fast the character moves. The view is responsible for updating the animation, and the control is responsible for receiving input from the user and passing the data along. And last time we had a cool discussion about is the view allowed to access the model and get data from the model. And it turns out that different programmer teams basically do different things here. Some teams do it the way that only the controller is allowed to access the model and the view, to send data and pass on along data. Some models allow the model and the view to observe each other, or rather the view to observe the model, which makes much more sense. And we're going to do that here, because otherwise we'll be coding a lot of getting data from the model into the controller and passing it along to the view, which is always a little redundant work, and I think it doesn't help us really in our quest to make a game fast and awesome. So we're going to allow the view to observe the model. And in our part, let's check out the view here. Let me zoom in a little bit. And in our case, this means the view gets the direction from the model each frame. So the function update direction is called each frame. So the view gets the direction. If the direction is not 0, then we want to pass the direction on to the animation, so the animation turns in the right direction. And then afterwards, so we only want to do this if the direction is not 0, because this way, if the direction 0 means the character is not moving at all, and if we don't change the direction when the character is not moving, then it will remain. It will look in the direction that we came from, basically, which looks a little nicer. So that's why we are doing this here, and then afterwards we are also getting the information from the model if the character is actually moving or not. We could use the direction value as well. If it's 0, it's not moving, but there might be different factors. The direction is actually passed along from the controller, so it's actually the direction the user wants to move. But later on, we could imagine that that the character freezes up, for example, because some ice spell hit him or something, and so the player wants him to move, but the model is frozen, so it can't move. So that's why we're getting this isMoving method here, so the model can control if the character is moving or not. So yeah, that's what we're doing every frame. And this data, as you can see here, we get access to our animator, which we referenced here as a public variable. So we can set in the Unity editor. and we did that here. Oh, so we don't have it on here. Well, that wouldn't help then. So let's make sure that we have our view on our character. We need that over here. So now we have the model, we have the control, and we have the view, each as a different component on our character. And we want to link up the animator here because that is a public variable. So let's link that up again, and I rename this visuals just so it's a little bit more clear. So this is the game object that actually has the visuals. Alright, and now if we hit play, you can see it will still just animate the move down thing, but you can see the parameters changing here. So actually, if you have the animator window open in Unity while you are playing, it shows you all that data, that live data, so you can debug your code or see if your code is doing what you want it to do. So as you can see, if I move up, the direction-y is changing to 1. If I move down, it changed to -1. The same with the x direction. And while the character is moving, the flag is moving is set to true, and if we're stopping, it's set to false. So we can use those data in our animator to play the correct animations. So at first, what I want to do is have the idle animation and actually make the character look in the right direction. What we tried last time is to create a subtree here, but that's actually not the easiest way to do it. The easiest way to do it is you can right-click, create state, and then create a state from new blend tree. So we have this blend tree here. We call it idle because this is going to be our idle animation. But what we can do with blend trees is we can double-click the blend tree, and now we're inside of the blend tree and can do other stuff. And in our case, we want to tell the blend tree that it should choose the appropriate animation, the appropriate idle animation up, down, left, or right, depending on where the direction parameters are set up. So what we have to do at first is we have to tell the blend tree that we want to look at 2 different variables. So we set this from a 1D blend tree to a 2D simple directional blend tree. And this way you have 2 parameters here that you can observe. We have the direction x, which is fine, and then we also want to observe the direction y. And you can see here that now we have 2 different parameters here. After we've done that, we have to set up the different animations that we want to play. In our case, these are 4 different animations. The character can look up, down, left, and right. So I add 4 motion fields in here. And once I added the second one, you can see that something new appeared here. This is basically just a debug view for you to see, to visualize where each animation is, because we can set the positions of the animations now. We can say this is position -1, 0. The second field should be played if the position is +1 and 0 on the y value. The third field should be used if the x value is 0 and the y value is +1, so basically looking up, and we do the same thing for looking down. And as you can see here in our debug view, we have these 4 positions set up now, so we can easily see this is supposed to be the up animation, this is supposed to be the left animation, so we can wire them up correctly. And yeah, and now we just set up our animations so that they're in the motion fields right here. Let's find our animations, which are in the lunk folder, and we can say, let's see, this is up, so we have idle up goes here, idle down goes here, idle left goes here, and idle right goes here. Yeah, and now you can see that the character, if we preview it down here in the preview field, it actually blends the animation together. Since this is a 2D game, there's not really any blending happening. The blending factor is more for 3D games, but it works for in our case as well, because you can see here, if I change the direction X, I'm looking from the wrong side. So here, if I change the direction X to positive, he looks to the left, to the right. If I change it to negative, looks to the left. And if I do the same with the Y value, then he looks up and looks down. So yeah, that looks way better. And now if we go back to our base layer from our animation here, we can set this up, this blend tree here, which is basically like a package of the 4 different animations, the idle, up, down, left, right. And we can set this as our default state. And if we hit play right now, you can see that the idle animation is playing, and if we move the character now, it actually displays the right direction where the character should be moving, which is amazing. And then we do the same thing with the move animation. So we have the idle over here. Idle is set up in 3 different animations, and then we do the same. Well, first of all, what I want to do when I press play, when I press nothing, right now he basically he looks to the left. Yeah, these assets will be downloadable. I've set up a GitHub, which I'll post the URL to that afterwards. Right now there's the last episode in there, and it's really not there's not much there, only the long characters in there. So after this episode, I will push the second episode to the Git, and you can have the link. But let me see if I can find it for you right now quickly. GitHub. It should be this. Yeah, there it is. So this is the URL to the GitHub, and right now there's only the character in there. And after this episode, I will put all the assets in there that we use today as well. And then next week I'll also push it to the Unity asset store. So you can use whatever you prefer, either clone it from the Git repository, or you can just get it for free from the asset store as well. Okay, so let's remove all these. We don't need those here, but we want to create another blend tree. Hi Kruno, thanks for joining us. Can set up another blend tree here. Let's call this walk, and then we basically do the same thing we did in the idle blend tree. We set it to a 2D blend tree. We say it should observe direction X and direction Y, and then we add 4 different motion fields. 4 different motion fields, and then we set up the position again. So we want to have right, left, and we also want to have up and down. And then we put the move animations in here. The move we set up the move animations last week. So this is move down, this is move left, this is move right, and move up goes in here. So the same thing. And now we have 2 different blend trees. The last thing that we will need to do is tell the animator when he should use the idle blend tree or when it should use the walk blend tree. And we already set up our parameter is moving for that, so we can use this parameter to choose which animation we want to play. And we do that by setting up so-called transitions. You select which animation you want to transition from. Click right-click, make transition, and click which animation you want to transition to. So we want to move from idle to walk, and if you click on the transition arrow itself, you can set up you can set up different conditions when this transition will happen. I'm actually using C# for this, but in Unity the JavaScript and C# are very close. So even if you just know you just know how to code JavaScript, you will still be able to follow this because I will explain everything. Okay, so we want to transition from idle to walk when the is moving parameter. So we can set up different conditions down here in the conditions field. And if you click the plus symbol down here, you can add a new condition. And each transition could have multiple transitions, but right now we only need one, and that is our is moving parameter. Note that those are all the parameters that we set up in our parameter list up here. So if is moving is set to true, then we want to transition to walk, and the same thing, we want to do the same thing backwards. We right click our walk transition, make transition, click on idle, so we have the arrow pointing in the other direction as well. And in this case we want to have the transition is moving. If is moving is false, then we want to go back to idle. So let's see how this looks. Press play here, and there it goes, moving. While it's moving, the walking animation is played, and this works in every direction. Perfect. So as you can see here, one thing is happening. So if we're moving, the character basically finishes his animation before before going back to the idle animation, and that's not what we want to do actually, because if as soon as the character stands still, we want the idle animation to play. And this is actually pretty easy to do. So we select our transition and we tell it that this transition doesn't have an exit time. If this flag has exit time is set to true, then it always waits for the exit time that we set up here before transitioning back. So we don't have an exit time, and you can also see that this transition has a length to it. This is useful if you have 3D models that can blend to each other, so the animation just doesn't switch but blends smoothly to the new animation. But since we have a 2D animation here, we can make sure that this transition is basically instantly. So we simply drag this right handle here and drag this as close as possible to the beginning, and so the transition basically happens instantly. And since it doesn't have an exit time anymore, it happens whenever you want. And yeah, hi. I'm not quite sure who you are from your name, but nice to see you again as well. Yeah, and we do the same for the other transition as well, for the transition from idle to walk. So we remove the flag has exit time, and we make sure that the transition itself is as fast as possible, so it's instantly. So let's see what happens if we press play. We walk and we stand still, we walk and we stand still. Perfect. So whenever we walk, the walking animation is played. When we're standing still, the idle animation is played. You can observe that up here, walking in every direction, and idle, which is perfect what we wanted, exactly what we want to do. So there's one other thing that I wanted to change. I mean, it works pretty well. I think maybe I already have changed it. Let me see. In the animation here. No. Okay, so the first animation of the first frame rather of the move animation is actually also the frame that is played in the idle. So you have, when you start moving, you have one frame that looks like the idle animation. So in order to move this, to make this animation look a little bit more to make this a little bit more responsive, we want to have the first frame actually appear like the character is already moving. So this is very simple to do. In our animation window down here, we just pick the first frame here, which is it looks like the idle frame, but we are actually in the move animation, and we just put it to the end of the animation and then move everything forward. So this way the first frame that is played is actually, it looks different than the idle animation, so it feels a little bit more responsive. It's just very small change, but still it's a little things to make this look beautiful. So let's do this for all the move animations. Oh, hi, Katie. Kati. I don't know how your name is spelled in English. I'm in English mode right now, but hi. So let's see. So we have the idle frame to the back, move everything forward, and we do the same for the down animation as well. Put this. So this way the animation feels just a little bit more responsive, which is nice. Okay, so now if we transition to walk, the walk animation is played immediately, which looks very nice. So it's very responsive now. There it goes. Awesome. So that was pretty easy. So we have two animation states. They're both blend trees. We have an idle and a walk state. We can transition between them, and both states have all the 4 different directions in them. And the state itself handles basically the view the character is facing, which is exactly what we want to do. Okay. So the next thing that I want to do today is create some obstacles for the character. So we want to have a little bit of level design here. The scene looks very empty right now, and for this I got some new amazing art from our artist Jesse. So you can see here, down here we have we have a bush, we have a chest that we can use later. We have a signpost. We have some stones. A big tree and a small tree and a tree stump, so we can use that to design our level a little bit, make it look a little nicer. And that is pretty simple to do. We basically just drag something into the scene. So let's drag a stone into the scene here, and as you can see here, let me move the camera back a little bit so the icon is not always the icon doesn't show it every time. Okay, so you see the stone here, and we can just place it in our scene, and I like to have it placed on the grid. And yeah, so one thing that you see is there's a head in the way. What do you mean by there's a head in the way? So yeah, we have the stone here, but it's a little the size is a little different than the character, and that is because yeah, I know this is a little bit easier because I actually do want to have the gizmos sometimes, but so yeah, but we talked last time. We talked about the import settings for each texture, and the stone texture actually has the pixels per unit set to 100, which is the default value, and our character has the pixels per unit set to 128, which is the size of the sprite sheet, of each grid of the sprite sheet. And I actually did some. I tried a little bit around earlier, and I found that I actually don't want to have 128 in here, but I want to have 64, and I'll show you why in just a second. And what this means is basically how many pixels on your sprite sheet is 1 unit in the Unity unit scale. So up here, if we have 0, 0, 0, and then if we move it 1 unit to the right, we basically moved it 64 pixels to the right. And I rather have 128 because I can show you here. If I select the stone and I do the same thing, I set this to 64 pixels per unit. This actually means that this stone is 1 unit large, which I like, because this stone is basically just a base unit size. So if I move the stone if I move it around, let's create a second stone here, and you see this stone is at -2 right now, and if I have it just 1 unit over to the right, so let's do it to -1 2, you can see that they're right next to each other. And I like that because the size of our textures, the stone is basically a base size, so the character as well basically has a width of 1, which is easier to recognize later in the code, because our grid is basically integer base, and we don't have these comma values if we want to put them next to each other. Yeah, so that's why we want to have it at 64, and Jesse actually creates the assets in this way that they are all in the same size. So the stone textures you can see here is 64 by 64, so this way one unit is 64 pixels. This is why. Okay, so yeah, so we can have and I want to do that for all the other textures as well here. So I have tons of different objects in here, and what we can do, we can just select all by pressing Command A or Control A. So we have all the objects selected, and you have all the import settings for those. So I want to have 64 in here, and now it imports the textures again, and now all these textures have this value set to 64, so we don't have to do it one after the other, which is a little bit tedious. So as you can see, if I put in the second stone here, it has the same size, or if we put the bush in here, it has the same size as well. So since the character had a pixels per unit of 128 before, he now got bigger in the scene as well. So we want to compensate for that by zooming the camera out a little bit more. So we just set we select our main camera, and it has this size parameter over here, which is set to 3 before. We just eyeball this value 3. It looked nice, and since the character is now twice as big, we just set this to 6, and it has the same size as before again. This is basically just a value that we just try out. We want to see how much do we want to see on screen. So this is very much a game design decision. Okay, so now we place some obstacles in the scene here. Let's see what happens if we press play. So we have the character. Oh, he actually moves slower as well now. So we have to increase the speed value as well, which makes sense. So let's increase this. I actually found out that the value of 5 looks nicer than 6. So 5 is a good speed, I think. So, but if we walk into the objects, actually nothing happens. The objects are drawn above the character, and we just walk through them. And this is because we have to tell Unity that that we cannot pass these obstacles. And in order to do that, we have to do a couple of things. So let me grab some water here. It's a lot of talking. So Unity has its built-in physics engine, and we want to use. You can use the physics engine for a couple different things. Like you can make a game where you work with gravity and stuff and stuff bouncing around. So you can use the physics for gameplay. But you can also use the physics for the collisions and making sure that that stuff cannot pass each other, or that you can recognize if some objects collide. So the physics can help us if the character actually moves through the bush and then triggers something. Maybe the bush just gets destroyed if we walk through it or something like that. So we can decide what happens, but the physics engine gives us some feedback which objects collide, and we can tweak it so that they work. It works like we want this to. And a physics engine, you wouldn't usually think that you can use it for a game like this, because we have a top-down view, and physics, it sounds like we have gravity and stuff like that, and we don't really have gravity here. So, but we can use the physics engine for a game like this as well, and I will show you how. So first of all, to use the physics engine, we actually add a new component to our object. We tell them that this is an active physics object, and in the physics language it's called a rigid body. And A rigid body is basically just an object in the physics simulation. Internally in Unity, the physics simulation is actually separate from the graphics representation. So we have to tell Unity which objects are used in the physics engine, because physicalizing objects is actually expensive. Not in our case, but if you imagine like a big physics game, it can be very expensive to calculate all the collisions between multiple different objects. So that is why we actually have to tell Unity for each object that we want to have represented in the physics engine. We have to tell Unity that. It's not automatically. And we do this by adding a rigid body component to our character. So we click Add Component, we search for rigid body, and you can see we have a rigid body and a rigid body 2D here. This is exactly what you would expect, because we're making a 2D game, we're using a 2D rigid body. And it ignores the z-axis, it only has x and y. And yes, I'm a self-learned programmer. Before I programmed in PHP and C++ actually, and then I switched over to Unity once I found out that I can work really fast in Unity and just make games. And yeah, it's an amazing software. We added our rigid body here, and if we press play now, you can see that this character is now handled by the physics engine because it has gravity and it falls down. We don't really want that, but this tells us that this character is now a physics character. So we don't want to have gravity, and in a rigid body 2D we have a value for that. It's gravity scale, and we actually want to scale the gravity to 0, so we don't want to have any gravity in there. And let's see what the other values here. We can set up a mass. We don't really need to do that for our game, because mass is actually used when two objects collide and when they push each other, which objects, it makes a difference how heavy the objects are. But we don't want to push objects here. We'll code stuff like that ourselves, so the mass really doesn't matter. Linear drag means how much friction the character has. So if the character goes like 10 meters per second, the higher the linear drag is, the faster he will go back to a full stop. So basically how much friction he has. And the same for the angular drag is, if the character is rotating, the higher the angular drag, the faster the rotation slows down and he stands still again. But since we're not using both of this, because in our game in Zelda it's like this as well, the character actually just moves and stops. So it moves at full speed if it's moving, and it stops immediately. So we're not going to use forces like that, applying forces to the character to make him move. We use it a little bit differently. So we don't need those values. What we do need is the fixed angle value. Because we don't want the character to rotate through the physics engine. So we say this character has a fixed angle, so it's always right side up. Is kinematic means that the character will not be moved by the physics engine at all. It just has a physics representation, but we will move him ourselves. And it will not be pushed by other objects and stuff like that. So we don't want to have that. Interpolation and stuff like that, we don't need that stuff now, so I won't go too much into detail. But yeah, so the gravity scale is set to 0 and fixed angle is set to true. So if we press play, you can see that nothing is happening, which is exactly what we want, because the gravity is not affecting our character anymore. So we can still move because we set this up before, but what we actually want to do is we want to change our movement a little bit, because now that we work with physics, we want to make sure that the physics engine knows about the movement as well. Okay, so let's go to our movement model, and actually I increase the speed to 5 again. I did that in play mode before. So let's open up the code to our model before. So as you can see here in our movement model, we basically just updated the position directly. but this way the physics engine cannot really work with it all too well, because if we just set the position, the physics engine cannot say, well, no, this is an invalid position, set it back, because we as the coders basically, let's say we have the last word. So in this case, we are setting the position and telling the physics engine, this is where we're going to be, and you have no say in this. If we please zoom the code, yes, I can do that. I think I have to remember to do that for each new file I'm opening, right? Yeah, okay. I try to remember that to set this up for each file. So yeah, so we don't want to actually update the position, but we want to use work with the physics engine. So the first thing that we do is we get a reference to our rigid body. And just like last time, since all these components, like the model and our rigid body, is on the same object, we can get a reference pretty easy to it. So we want to have a reference to our rigid body 2D, rigid body 2D, call it mbody, and we setting up this this reference in our awake function, because this happens immediately when the object gets created. So we say mbody is equal to get component rigid body 2D. Yeah, rigidity body. Yeah, it's a rigidity body. No, rigid body 2D. So yeah, so this way this variable stores a reference to our rigid body here. The next thing we want to do is we don't want to set the position of the character or update the position. We actually want to update its velocity, because this way we're telling we are not saying the character should be at this position now, or if it's moving right, we are not updating the position. We're actually telling the physics engine it moves at this speed to the right, and this way the physics engine can override this and say, no, here's an obstacle, we can't move to the right, and so the character will stop in front of an obstacle. So instead of setting the position like here, we are going to remove that, and we access our rigid body and set the velocity, and we set this directly. And this way the velocity is set instantly to the speed that we wanted, so it will be set instantly to 0 if we are not moving anymore, and will be set instantly to our direction we want to go without any lead up or acceleration in there. So we want to set it to the movement direction times speed, just as before. There's a little difference here. As you can see, before we multiplied this value times delta time. But this is actually, the physics engine will do that for us. We're actually saying move at 6 meters per second to the right, and then the physics engine will figure out how fast this is each frame. So we don't need to multiply this, actually. The physics engine will do that for us. So we remove this, so we set the velocity, and we have to change our code a little bit up here. Because before we said if movement direction is 0, we just return, so we don't change anything. But if the movement direction is 0, we still want to tell the physics engine that the movement direction is 0 now. So we changed this to if movement direction is not 0, and then we put this normalize in here. What this means is basically, if the movement is not 0, then we want to make sure that the movement direction vector always has the length of 1, because no matter in which direction we go, if we go diagonally, basically it should be 1 as well. And then we multiply it by the speed, so no matter which direction we're going, we're always moving at the same pace. And we cannot do this if the vector is 0, because normalizing, if the vector is 0, you cannot normalize it, because normalizing means set this vector to a length of 1. But if it has a length of 0, there's no way to know what a length 1 vector is from that. So we can only do that if the movement actually has a direction. And if it's 0, we want to keep it that way. We want, if the movement direction is 0, we want it should stay 0, so that the velocity is then set to 0 as well and the character stops. Okay, so let's see if that worked. Let's press play here. And then we move the character, and perfect. The character is still moving, and basically nothing has changed visually, but we know we're using a different movement model. So now we're using the velocity instead of just setting the position directly. But as you can see, we can still move through the objects. And this is because we only told Unity that our character is a physics object, but the objects are not physics objects yet. And also the character doesn't have a size yet. We also have to tell Unity what the dimensions are. And this is also for optimization purposes. It's in most games it works like this, that each complex 3D character actually has an invisible, much simpler model, usually just made out of boxes and stuff, that represents the physics. Because it's much easier to calculate a physics collision with a box than it is with a complex character that has curves and holes and stuff like that. And this physics representation is called a collider. So let's make sure that we add a collider to our character. We don't have a diagonal animation actually. We only have up, down, left, right. And this is how it worked in Zelda 3 as well. There were only 4 directions, and if you move diagonally, it basically used the last direction that you moved in. We don't have that in yet. We can polish that later, but yeah, there's only 4 directions, because just making 8 animations for everything, like if you have an attack animation, then you need to make 8 animations. If you have a hit animation, you need to make it in 8 directions, stuff like that. So it's tons of work. So we just use 4. Okay, but we wanted to add a collider. So let's have a collider here, and you can see there are tons of different colliders here. There are 3D colliders and 2D colliders, a circle collider, and stuff like that. But we're content with just using a box collider. And as soon as we added the box collider, you can see that there's this green box here that represents our collider, and the dimensions are not quite correct, so we can click Edit Collider here on this button, and then you see that the collider actually has some 4 new handles here, and you can just move it around like this. So let's put it like this. Make sure it's approximately the size of our character. And as I'm saying, the physics engine is always just approximately like the actual character, just to make it easier to calculate all the collision stuff. So yeah, so this is the physics collider of our character, and now we also want to have physics colliders for these objects. And to do this, I'm actually going to let me remove these once more, and let's just use the bush for now. But I want to create like one layer of abstraction for the bush, because I don't want to. What I usually do is split the collider and the visuals from each other, and I'll show you why in a second. So I create a new game object, and I call it bush. And let's put it at 2, 0. And I make sure that the bush intact, which is our visuals here, is a child of that object. And we set it to 0, 0, 0. So it is at the same position as the bush object here. And so now we can add a collider here, and I'm also going to use a box collider. I could use a circle collider because the object looks kind of like a circle, but in Zelda, if there are 2 objects next to each other, you can they act like a wall actually. And if we use a circle, then you could like slide into a wall a little bit, and it doesn't look as nice. So we just use a box collider for this as well, and I make it a little bit smaller than 1, 1, 1, 1. Just a little bit, but yeah, you can see. So this object has a collider as well. And so, and now I can show you why I separated the collider and the visuals. Because let's say I want to change the visuals, like if they have tons of bushes and I want a little bit of variation, I can now just rotate the visual object, and the collider, the physics actually stay the same. So this way I've separated them from each other and I have more control. So and I use this method in 3D and 2D as well. So I always have a base object, and the visuals are always children of this base object for this exact reason. Because then I can just rotate the visuals and the object itself doesn't change. Okay, so our bush has a collider, our character has a collider, and our character is a rigid body as well. So it's a moving physics object. If an object only has a collider without the rigid body, it means this is a static obstacle. This is an obstacle that will not move in the physics engine. And this is way cheaper to calculate for Unity, because it doesn't have to make this object move as well. It knows it will just stay the same all the time. So that's why we don't add a rigid body here, because we don't want this object to move at all. Okay, so let's press play. And let's maximize it here so you can see it properly and walk around. And if we walk towards a bush, then we are still moving past the bush. Okay, so what is going on here? Oh, thank you very much. Yes. So this is a problem. I used a box collider on the bush, and since we're using 2D physics, I have to use a box collider 2D. Thank you very much. I kind of wasn't seeing it, because if something goes wrong with your life, then it's hard not to panic. Okay, so we need to use a box collider 2D in this instant, because we're using 2D physics. And I'm making this smaller a little bit again. And so let's see if that fixed it. Press play here, and there you go. Okay, so now you see the character is walking. It's still playing the walking animation, but it will not pass our obstacle that we created. Cool. This is a good first step, but there are a couple of things that we want to improve. So for example, if we collide with the object, oh yeah, let me talk about fixed update for a second, because you brought it up in the chat. You're right. So there are two different update functions in Unity. One is called just update, and the other one is called fixed update. And the difference is that update is called every frame that you render. So if your game runs at 100 frames per second, the update function will be called 100 times. And fixed update actually is not called every frame, because the physics engine is also not simulated every frame. You can see that if you go into the settings, project settings, and check the physics, no, it's in physics, I think, not in physics 2D. Maybe not, or somewhere else. I don't know. You can actually set this up. The physics engine is actually simulating, I think, like 30 times a second, or 60 times a second. But it's not running every frame, and this is the same reason as why we have colliders, simple colliders, because physics is very expensive to calculate. If you imagine a huge complex project, so physics is actually stepping at a fixed it's called a fixed amount of times per second. I think in our case it's like set to 30. So the physics engine is called 30 times a second. No matter how fast your computer is, no matter how many frames per second the game runs at, the physics is always called 30 times per second. And in order to work with the physics engine, because your update is is used more often than the physics update, you have this fix update function, which is in sync with the physics engine. So fix update is called every time the physics engine actually updates. So in our case, 30 times a second, no matter how fast your game runs. 150 is the default. Yeah. So okay. So the physics engine runs at 50 times per second. And yeah, so imagine if you add a force to an object. So you want to push an object and you add a force to it. If you run it in the update function, you actually, if your update function is called more often than your physics function, your physics update, you can actually add this force multiple times before the physics actually does something. So there will be some wonky behavior there if your frames are fluctuating, because some regions of your game are more complicated, so you have lower frame rate and stuff like that. It won't always be the same. So this way you can use the fixed update, because you know it's always running in sync with the physics engine. So yeah, whenever you manipulate stuff in the physics, be it velocity or adding forces to something, making stuff rotate with physics, it's recommended to always use the fixed update. In our case, it's actually not that bad, because we're just saying the engine, the velocity is a fixed amount right now. So it doesn't really matter, because the character is actually either moving at a speed of 6 or a speed of 0. But it's recommended that you use fixed update whenever you are working with physics. Late update, late update is actually called every frame as well, but it's called after all update functions of every object in the scene is called. So you don't actually know, if you don't tell Unity in which order your update functions should be called, you don't actually know in which order they're called. So if you have 3 different game objects and they all have different update functions, you don't know which update function is called first. And sometimes it's important to know that. And sometimes you just want to do something after all update functions have calculated. You can use it for GUI stuff like you guys suggested, for example, or if you want to update a statistic or something. If you want to make sure that all the update functions have been called and all the positions, for example, of your objects have updated, and then after that has happened, you want to store those positions in your statistic, for example. You can just use late update, and late update is actually called, so if you have object 1, 2, and 3, the update function 1, 2, and 3 is called, so update on object 1, update on object 2, and update on object 3, and then the late update is called on the object. So you have update, 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 late update, late update, late update. So you know it's always after the update functions. And if you need even more control than that, if you need to define specifically which update function should be called first and stuff like that, you can do that as well. I just show you quickly. I don't want to go in too much detail here. So you click a script object, and then in the top right corner here you can see the execution order. And if you click that, you actually have a list. You have a default time, which is the random Unity time, which Unity can decide whenever the update function is called. But you can also drag your object in here and say this is, if it's above default time, it's called before. So we see here that our character movement base control, the update function, if this class has an update function, it will be called before all other update functions. And if we drag it below the default time, it will be called afterwards. Sometimes you have different classes and you need to make sure that they are called in the correct order. So you can use the execution time for that. Yeah, please go ahead. I think I know which image you're talking about, so please go ahead and post the link here. But yeah, right now we don't care when which update method is called, so we just don't use the execution order. Okay. So the first thing that we wanted to do is when we collide with our object from below, you can see here that we cannot pass through the object at all. But in a game like this, you want to kind of fake a perspective, because you can see that the head actually shouldn't collide with the object. Actually, just the feet of the character should collide with the object. So let's click our character again, and let's change the collider actually, and not use the whole character as a collider, but only use the bottom part here. Let's say, for example, like this, and then drag these in a little bit as well. So we basically just use the character's feet as a collider. And when we press play now, what we can do is that we can actually, the same thing happens if we move to the character from the top and from the side, so nothing really changed here. But if we collide with the object from below, we actually run into the object. You can see here the bush is actually drawn in front of the character. We want to have it the other way around. We want the character to be drawn in front of that. But this is actually what it's getting there. So the basically just the character's feet are colliding with the object. So let's see what we can do about this. We want to tell Unity which object is drawn in front of what object. To do that, the 2D part of Unity has something called the sorting layers and the render order. You can see this in the sprite renderer here. You can see a sorting layer and order in layer. Right now, our character is set to the default sorting layer, and the bush is also set to the default layer, and they are both set to 0, so they're rendered at the same height. I mean, a 2D game doesn't have a height, but if you can imagine, the sorting layer basically makes sure which character is drawn in front of what, or which object is drawn in front of what. And since both are at the same layer and at the same order, the order in the hierarchy is actually used. But we want to have a little bit more control. So what we do is we create a new sorting layer. So let's click on layer here. You can click on layers on the top right corner here. Click edit layers, and there you have the layers, which is something different, and then you have sorting layers and tags. And sorting layers is what we want to use here. Yeah, you can see that you have the default layer here, but we can add new layers as well. So we add a layer to the list, and we call it characters, because we want all our characters to be drawn on the same layer. And then we have ground objects as well, and we want to draw the ground objects below the characters. So basically what this does is, if we set up the sorting layer on one object, they are drawn one after another. First the default objects are drawn, then the ground objects are drawn, and then the characters are drawn. So now we have to set up our renderers. So let's click on the bush renderer here, and you have your sorting layer, which is still set to default, and we set this to ground objects. And we do the same thing with the visuals of our character. We have our sorting layer, and we set this to characters. So let's press play. Yes, this tutorial will be put on YouTube. The channel name is Let's Code Games. You can find it. Let's go to YouTube, and then I'll post the link for you. Search for Let's Code Games, and then there's the channel here. I'm still rising to the top, but yeah, this is the second week, but so we'll get there. And I don't actually have a short channel URL yet, so I'm working on that as well. So this is the URL for now. Okay, back to our game. So we set up our sorting layers, and we can walk around. And as you can see now is, when we collide with the, let me hit maximize on play here, so it's bigger and easier to see. Once we collide with the bottom, you can actually see only the feet are colliding, and we're basically moving into the bush object a little bit. But this gives the illusion that we're like a tall character. This is how 2D games that have a perspective from the top basically work. Like give the illusion of perspective a little bit. But this looks pretty nice actually. Cool. Okay, so what we can do now is we have actually tons of different objects here. So we have our stones as well. So let's create a stone. And the stone is actually, for now, it's actually the same as a bush. So we just duplicate our bush by pressing Control D or Command D on a Mac. You duplicate it, so we have a bush 1 here, and we call this stone 1. And we want to move this stone 1 a little bit. It still has the bush object, and what we are doing here is we call this stone small 1. And then in the renderer we still have our bush sprite attached to the renderer, and we just take our sprite and move this over into the sprite thing. So now we have a stone, and the stone has its physics objects, and we want to create like stone 2 and 3 as well. Let's move them a little bit. Stone 2 and 3. Let's rename those as well. I mean, that's why I usually, well, let's do this. That's why I usually call these child objects visuals, because if I change the sprite, I don't want to change the name of this child object every time. So let's just call this visuals. It's much easier. So stone 2, we set our stone 2 in here, and then for the visuals of stone 3 we set the 3 in there. So now we have 3 different stones, and they're all physicalized. Isn't Unreal better than Unity? Well, it's just different. There's you can go into a huge discussion, but that's usually people just get mad and stuff like that. There are 2 engines. Use whatever engine you like. If you want to make games, use whatever engine you can use to make games. There's really not much difference there. Okay, so we have our stones in here, and those stones are obstacles as well, and we still have our perspective trick here, so it looks like the character is actually standing up. Yeah, awesome. But and then we can do the same thing for our tree. Let's put our big tree in here as I duplicated the stone again, but I want to have the big tree in the visuals, and the big tree actually is bigger than a stone, as you can see here. So it wouldn't make sense for it to have the same collider, because look what happens if it still has the collider. You run into the tree and you only collide with the center bit here, which is not what we want to do. We want to collide with the whole tree actually. So we click on our tree. In our Collider 2D we click on Edit Collider, and then we just move these so they're a little bit better aligned with what the tree is. Now as you can see here, this object is actually a little bit difficult to just use one box collider here, because at the bottom here it wouldn't look very nice. So what we can do is we can just use multiple colliders to make it look a little better. So I use this one collider, make it very small, just to have this root object represented here, and then I create another box collider 2D. And I'm curious right now if this works like I expect it to. We'll see. Or if I have to make a rigid body from this for it to work. But yeah, let's try it first. So we have 2 colliders, and we run against this one. Looks good. And then we can run against the root. Yeah, perfect. Yes, you're right. We can also use a polygon collider. And I mean, it's a good opportunity to use a different collider than box, but you can use a circle collider up here to approximate this tree top a little better. But you can also, if you remove those again, add a collider, and this time we use a polygon collider. And what this does is actually it lets us draw an approximate shape of the object. So if we added collider, you can see that we have, like, this is this has 5 corners right now, but if we click into the center of one of those, we actually add a new vertex here. So we can make a rough approximation of this object here, without having to resort to different colliders, which is a little nicer, and we can also approximate this a little bit better than just using 2 boxes. Computationally, this is a little bit more expensive, but in our case, since we are making a very simple 2D game, we don't have to care about how expensive it is. I usually, even if when coding my 3D games and they have tons of different objects, I don't think about optimization so much until the game is running too slow, and then I'll fire up the profiler, see which parts are slow, and I optimize those parts, because it's just optimizing everything is expensive. It takes up a lot of time, and if it doesn't need to be optimized, if it's not running that slow, then you don't need to profile it. But this is looking actually very nice, so this is a good approximation of our tree. So if we press play here, you will see that we can run a little bit closer to this edge here, and it actually works pretty nice. I mean, I think we can improve this bit a little bit because it's looking weird. If you move to the left here, this is looking nice. I think we can just improve the right side a little bit by clicking the big tree, edit collider, and then moving this bit over here. I think this is better. Like this maybe. Okay, good. So this is our big tree, and we have a new collider for it, which is pretty nice. And then we can have multiple instances of this tree, just duplicate it, and then we have like a little tree line. I think in Zelda they do it like this as well. They have the trees a little bit spaced out, so it looks nice. So we have a tree line over there. And we can continue to do this for all the objects that we have. There wouldn't be much difference here. I think we still have a smaller tree. Let's duplicate the bush and call it small tree. Add the visuals in here from the small tree. And it's also a little bit bigger. For this, I'm just going to use a box collider, because in the old Zelda they didn't have these fancy polygon colliders we have here. They actually had square tiles, and they just said, "Can you walk here, or can you not? Can't you walk here?" So actually, they would have basically one box collider for the whole big tree. So we can actually make it nicer than the old Zelda 3. So we have small tree here. We can have a tree stump as well. Tree stump. Set this up. It would be cool to make the character go behind the leaves part of the tree. That is a very nice suggestion. I mean, yeah, it would be cool if you could imagine, if you think about how the tree looks. Basically the roots part, the trunk is down here, and you should be able to walk past here because of the perspective, right? And we can do that. But our problem is we're using the perspective here, so the character is drawn above. So if we just remove the physics part here, then the character will still walk above the leaves. So if we want to do that, like you suggest, then we actually need to separate our tree into two different objects. The one that is drawn below the character, which is the lower part here, and then the part that is drawn above the character, so we can walk past it. And I can prepare that for next time, so I can create the assets so we can do that. I just don't want to spend any time in Photoshop right now and just splitting them up. It's not hard to do. It take a little bit of time and making sure they align properly. But yeah, for next time I will prepare the trees in this way, so we can set this up in this way as well. It's a good suggestion. It will look really nice actually. You can play a little bit of hide and seek in the game. We can also do this via code. And to Y-sort them, yes. You could also Y-sort them, it's true. Let me think about it a little bit. Yeah, we could write a piece of code that basically sets the order of the object depending on where it is on the Y-axis. So the higher the move, the farther back in the rendering order you get. But this way, you have to. There are all these different edge cases because if you just use the center position of the object, it might work with the tree because our character is the center object of the tree is here, around here. So now the character would be drawn above it as we expect, and now it would be drawn below it. That's what we want. But for objects like these, for example, you might have the problem that this breaks, and you always have to check the different objects. So I actually like it better to separate these objects because I have much more control like this, where the character is split up and which parts are drawn above and which parts are drawn below the character. It's just personal preferences. Yeah, but for stuff like this, I actually don't want to code it just to have more control over it. Yeah, I mean, yeah, you're right. And this is actually, since the visuals are child objects, it's actually pretty easy just to adjust the pivots. But still, I think it's just way easier. It's not way easier. You're right. If we code it correctly, it might be easier to set up. But I don't know. I still like to have the control of it to actually say this part is above and this part is below. Because this way I have control. I can do some fancy stuff if I have curved objects and stuff like that with stuff coming down from it. I can actually say in Photoshop, this is the part that is rendered above, this is rendered below. I just have much more control than just one break off point when the character will be below it. It's just personal preference actually. So in games there's always 1,000 different ways to achieve the same effect, and you just have to decide what you want to do. Okay, so now we have our stone, our tree stump, and we also have a chest and a sign. And we still have like 30 minutes left, so the chest and the sign are actually interesting because we could make the character interact with them. So before we do that, let's create the sign and the chest. Sign. And chest. Go over here. And we can just copy all those trees and put them on the left side as well. So we basically have a little bit of a border around our level, even though it's still not perfect, but it just looks nice. So we have our sign, and where's the chest? The chest is still here. So the chest is interesting because the chest has actually different states. It has the closed chest and the open chest. For now we just set it to the closed chest, the visuals, but later when we interact with it, we actually want to switch that state, so it will switch to the open state once you open the chest. So that's interesting. And the sign, we can interact with the sign by making it say something. I'm not sure if we're able to make it display text on screen today. That might be a little much, but we can just start the interaction system and then see where we go from there. Okay. You would like to see implementation of both. Well, we'll see. I mean, yeah, it would make sense since this is a tutorial. I may think about it, and we'll see what we do next time with this. Good. Let's duplicate those as well. No, that doesn't make sense. Let's duplicate. Nope. Those again. Put them down here, and then actually move everything. Let's sort this out a little bit. It's getting a little bit crowded in our hierarchy here. So I create a new empty object, put it in the center, and I just call this the environment. Let's do the trees. Well, yeah, we have environment, and then I have another empty object with the trees, or let's say big trees. And now I can put all the big trees in here, and it basically acts a little bit like a folder system. So we have everything nicely separated. So this way I can have all the big trees here. Let's move them up a little bit, and then duplicate this one and this tree 3 and tree 2. Duplicate those again, put one here, so we actually have complete sides to our level. Just nice. And now I can just close this, and I have all the big trees hidden away, which is nice. So we have it separated a little bit. Small objects. I create a folder for all the small objects. Make sure it's in the center. And then I put everything else in here. The bush and the stones. Small tree stump. Put it in the small objects as well. Okay. And then we leave the chest and the sign here. Oops, nope. Chest and the sign here for now. And before I saw there are some problems with the roots, and I see what you mean now. The two top ones are actually quite funky, and this is because they're just not in the right order here. I mean, what's happening right now is exactly actually what we talked about before. The objects are all on the same order, and actually you can since they're on the same layer and on the same order, it's basically you can't really affect where these objects are rendered. So you see, when I delete an object, then this object pops to the front all of a sudden. So it's actually in order to fix that, we have to do what we talked about before, and change the Y order actually of the objects depending on where they are. And I'm debating right now what we want to do first. I think it's better to fix the order of the objects before going on to the continuing on to the interaction stuff. I mean, we could for now. So first thing we need to do, let's see that we have that we know. So this object is on the right, this is on the left, just so we know what we are working with. This one is on the left as well. This is on the left, on the right, on the right, right, left. Yeah, we have tons of code as well. So, but right now we are basically just working with physics, which is very visual, and then we're going to code our own stuff later on. So let's move all the right stuff to the top, so they are under the there you go. And then we put them in the right order. So this is right 1, this is right 2, write 3, write 4, and write 5. And what we can do now is basically they are all on the same. The visuals are all on the same sorting layer. They are all on ground objects, but the order in the layer is always 0. So Unity basically renders them whenever it's ready to. They're ready to render. But we want to make sure that these objects are rendered in the order that we want them to be rendered in. So what we can do is, I'll move this down here. We can just tell Unity in the order they should be rendered in. Wait a second. Let's have them 1, 2, 3, 4, and 5. So actually, we want to draw the object that is the farthest away. We want to draw this first. So we say this remains on order and layer 0. The next one is drawn above of that, so it gets a higher number. So you see here we put this to order in layer to 1 now, and so this object, the second tree we're editing right now, is now in order 1. All the objects are in order 0. So you saw the roots popping out here because this third tree is still on layer 0. So we do this for all the objects. Add one here, add one here, put this to order 3, and put this to order 4, and now they're in the correct order, and we actually told Unity what the order is. This is actually very cumbersome to do that by hand, but for now we do it this way. Later on we will design some tools that help us do that, so we don't have to do this manually every time. But for now I just want to get to the good stuff. So let's see that we name them properly here. This is L1, this is L3, this is L4, L5, and this is L2, and this is L2. And so we start with 5 at the top, 5, 4, 3, 2, 1, and then again we use the order in the layer. This is 0, no, other way around. This is 0, this is 1, this is 2, 3, and 4. So now all the trees, they look perfect, just the way we wanted to, and this is basically what you can do with the order in layer. So the objects are sorted first by the sorting layer. So no matter how large the sorting in layer value is, if the character, so let's put this basically to, let's say 5,000. So this tree here is on layer 5,000 now. So it's above all the objects, but you can see it's still below the main character. And this is because the main character is on a different sorting layer, which is always above the ground object. So no matter what the order inside the layer is, the character's layers is always drawn in front of our objects, which works for now. Later, if we want, later we can create an now we have the ground objects layer. We can also have like an air objects or like another objects layer that is above the character, where we can put stuff like the treetop or a high tower, so the character will walk behind them. Okay, so we fixed our sorting problem, and now we want to interact with the objects. So we actually only have 10 minutes left. So what I want to do is just to get the basic idea of the interaction, and then probably we're going to continue with that, with doing the interaction stuff next week. So as I said before, to interact with something, we need to listen for input from the player. We need to stand close to the objects, and we also need to face the object. 1 second. So let's start with the input part, because that is pretty easy. So we have our character movement keyboard control. So I called this component character movement keyboard control, which is actually, now that we listen for other stuff as well, I think I'm going to rename this. We just rename this into character movement base control, character base control, and character keyboard control, because I don't want to create a new controller class for every single model and view part. I think we can have a controller for the character, and then later we can also have a controller for the enemies and stuff like that. Does that make sense? Let me think about it, how we could set this up properly. Yeah, I think we put the controller into one class. Hey Bob, glad you could make it home. I actually made sure that I checked the save this stream this time, so you will be able to see it later as well. Okay, so let's get into our control part here. And so right here we have to rename this class as well now, because we called it differently. So rename this, and then rename this movement base control as well. What? So command. Okay, right click. Refactor. There it is. There's some bunch of new stuff because I installed a new plugin here. So rename it. We rename this character base control, because we renamed the file. Okay, and because we refactored, we just didn't change the name, but we right click, refactor, rename. Because we did that, the Visual Studio actually changed the name wherever it appears. So if we go back to our keyboard control, you can see that character base control also has changed. So if you rename a variable, it's always better to right click, refactor, rename it. So this way you don't have to manually rename it everywhere in the code where this variable is used. Okay, so keyboard control. We actually let's see. So every frame we want to listen for the spacebar. We name this function update action, and we do something similar like update direction. And this is a very simple way to do it, very direct way. Later on, we want to don't want to hard code all these values like WASD, but we want to put them in Unity's asset manager. But for now, we just do it like this because it demonstrates very directly what we want to do. So if input get key down, in this case we use get key down, and get key down only triggers the instant you push the button, whereas get key always returns true as long as the button is pressed. So that's the difference here. So get key down, key code, code space. So you see, if space is pressed, basically, then we want to do something, and we need to make sure that we call this function. So we put this in the update function up here. Okay. So what do we want to do? Whenever we press space, we want to interact with different objects. And for this, I want to actually create a new as you can see here in the update direction, we set up a method set direction in the base class, in the base control class. So the keyboard control is inherits from the base control class, and we do it because I want to be able to switch the keyboard control later very easily for example, a gamepad control or a touch control. But I don't want to set up the communication with the other stuff in the code every time. So I'm using the base class to basically set up the communication with the engine, and then the different controllers like the gamepad controller and the keyboard controller just call these functions in the base class, which then communicate with the rest of the code. And this way it's very easy to create a new controller later on, and we know that it always communicates the same way, because we never interact with the rest of the game from the keyboard controller or from the gamepad controller. We always use the base class to communicate with the rest of the code. Okay, good. So yeah, as I said before, we're checking for the key space, and then we want to do something. But doing something means interacting with the rest of the code. So that's why we're doing the interaction in the base class, because then we can use it in a gamepad class or in a touch class as well. So protected void, and we call it on action pressed. And this doesn't need a parameter, because this is basically was it pressed or wasn't it pressed. So on action pressed, and we make this function protected, so we can call it from the child classes, but we cannot call it from the outside. The keyboard control can call this function, because the keyboard control actually inherits the base control. This way we can. This is what protected means. So we can in the keyboard control we can call this function on action pressed. And now we can go back to the base control, and in this we will set up the whatever we want to do. And if we interact with something, in Zelda 3 there's no animation in there, but you could imagine, like in future Zelda games like Ocarina of Time and stuff like that, you always have this animation, and Link opens the chest and goes in there, so an animation is played. So this is actually, we would communicate with the view that we're interacting with the chest now. Actually, we're just on action press. We don't even know yet that we're interacting with the chest. So we still need to do some more stuff. We don't, but it's not visual stuff. We need to figure out what we are interacting with and stuff like that. So that's why we need to communicate with our model. So we have our movement model here, and I want to have an interaction model as well, so we can interact with stuff, and we have the movement and the interaction separated. So let's create a new class here, and we call it character interaction model. So all the stuff that interacts with different parts of the game is in this class right here. And actually, I would encourage you to use many components as well. If you have like a huge logic block like interaction and movement that is completely separated, I would encourage you to do two different classes for that, because if the class just gets too long, it's very hard to navigate stuff. It's easier if it's separated, and also it's easier to reuse the class later on. So maybe a character can move, but it cannot interact. So this way you can put a movement model onto the character, but you won't put a interaction model on the character. And actually, if you think about doing it this way, you would always have to check if the model actually is set, because imagine, so we have a variable movement model now, but we also want to have a variable character interaction model. But if you want to have it this way that that you maybe don't even have the interaction model, or maybe you don't even have the movement model, because there may be a character that can interact but it cannot move. Well, the other way makes sense, a character that can move but it cannot interact. this would be, you just wouldn't put an interaction model component on that character, and so this variable would be empty. So we have to check for that first. So if the interaction model is null, oh, I have to zoom in again. Let's zoom in again. How do you open your Unity project in Visual Studio? Well, once you create your first script codes, let me open the project folder here. Here, Unity projects. Here. Once you create your project and you have the first script file in there, Unity actually creates solutions for you and project files for you. So you can just open those with Visual Studio. The same files that you use in Mono Behavior, those are the same files that are used in Visual Studio. So just open them in Visual Studio. And then if you want that to happen automatically, if you double click a file, for example, you can set that up in the preferences. Go to Edit, Preferences, and then click on External Tools, and right here you can set up the external script editor, which you can see I have set to Visual Studio 2013. You can also use MonoDevelop and other code editors, stuff like that. So you can tell Unity which code editor you want to use. You can do the same thing. You can set up Photoshop here, so images are always open in Photoshop and stuff like that. Yeah. Okay. So let's back to our model. So we check if the interaction model is 0. So if there is no interaction model, then we don't want to do anything actually. And we want to do the same with the movement model just to be safe. If the movement model is 0, don't do anything. Hey, Mr. Hot and Spicy. Unity 5 is completely free, yes. Completely free. So you get the same feature set. So in Unity 4 you had Unity free and a pro version. In Unity 5 you don't have a pro version anymore. In the free version you get all the features. And there are some stuff you get in the pro version, like team feature functionality and access to Unity cloud services, stuff like that. But you can, everything that I do here, you can do with the free version of Unity, so you don't have to pay anything. And yeah, actually, I mean, we have 8:05 now, so actually we're at the end of our tutorial. And it's better to stop now and just make the interaction model next time, so we don't have to stop midway. We can just do the whole thing in one stream. I think it's way easier to do it this way, and just has a nicer split in here. Okay, so just to recap a little bit, what did we do today? First of all, let's press play so we can play our game in all its glory. The first thing that we did is that the character... Oh, I want to change one thing. So if I press play, you can see the character is looking to the left, and I don't like that. I want him to look down. So in the movement model, in the start function, and just quickly, the difference between awake and start is awake is called immediately when the object is created, and start is called when the first frame is rendered. So awake is called before start. So I use awake to set up my references, so I make sure that they're set up all the time, and I use start to do my initialization code. It's just a good way to separate those. So in the start function, I actually want to set the... No, not call start function again, that doesn't make sense. Call set direction, and in the beginning I want it to set the direction to mu, no, not mu, new vector 2. Is it a 2? Wasn't it a proof? Oh yeah, it's a vector 2. And I want him to look down in the beginning. So when we press start, the character is facing us, which is just way nicer. Press play, so the character is facing us now. Nice. So what did we do today? First of all, we made sure that when we move the character, the movement animation is playing and it looks in the right direction. Then we started working with the physics engine and made sure that our character is represented by physics. And then we added all these obstacles and gave them physics objects as well, so the character doesn't move, cannot pass these objects here. And we used a small trick to use this perspective stuff, so it looks like the character is standing up a little bit, which is very nice. And then what we also did is we learned a little bit about sorting layers and the sorting order. So we can tell Unity in which order the objects should be drawn, so that objects that are further behind are actually drawn behind objects that are closer to the camera. Closer. I mean, we're looking from the top, but as you can imagine, we're actually not looking quite from the top, but a little bit slanted. So this is why we see the body of the character and then the tree, the roots of the trees as well, and stuff like that. So yeah, that's what we did today. And next time we want to make sure that we can interact with the objects here. So we can interact with the chest, and we can interact with the sign. And what we can also do next time is like we get something from the chest. So we still have objects we have tons of different objects that we haven't used yet. So for example, I have a shield for the character, so we can do that next time, so that when we interact with the chest, we actually get a shield, and then the character runs around with the shield as well. I think that's a cool thing to do for next time. I mean, I also want to prepare the trees so that we can walk behind the trees a little bit, which would be very nice. And yeah, I think that will be more than enough to do for next time. I think that should be it for today. Thank you all for watching. We actually have 42 viewers now, which is pretty awesome. Thank you all for coming by. Alright, yeah, so that's it for today. Again, thank you all for coming by. And I hope to see you all next time. Or see you on YouTube. If you have any questions, just post a comment on YouTube, or wait till next time. I'm also on Twitter at twitter.com/letscodegames. It's very easy. It's always the same name. I was very happy that all the same names I was able to get all the same names on all the channels. So twitter.com/letscodegames. You can follow me here if you have any questions. I mean, I have 6 followers. I need more followers on this Twitter account. So yeah, please follow me on Twitter. And other than that, I will see you next Saturday at the same time. Other than that, code some games and have a good week. See you next Saturday.